Welcome to this tutorial on the Serve Research Cloud. There's timestamps in the description if you want to jump ahead to your topic of interest, and otherwise there's links in the description and links to resources where you can download some code, the PowerPoint I'm going to present, and of course also more documentation to help you on your way if possible. Then for those who are actually staying around here, I'm Fabian. I'm a researcher at the University of Applied Science in Utrecht, the HU, Hogeschool Utrecht. And I'll be taking you through what the Serve Research Cloud more or less is, what it can do, how you can set it up, and through a practical example also show what it can do in practice. This will all be done through the lens of working at the HU, the Hogeschool Utrecht, but wherever possible I will generalize to other educational research institutes within the Netherlands. It should largely be generalizable, but I'll give you hints when necessary. So today we will be going through the what, the why, and the how of the Serve Research Cloud. To start with, for those unfamiliar, Serve is a cooperative association of Dutch educational and research institutions in which the members combine their strengths, utilizing and developing shared IT infrastructure and services, amongst which is the Serve Research Cloud. The Serve Research Cloud's purpose is to grant cloud computing capabilities to those who need it. This means that your data or your models no longer run on your local device, like your personal laptop or desktop, but that they run on a computer or server elsewhere that you're connected to via the internet. The benefits of which I'll list in a moment. Specifically, what the Research Cloud offers are virtual collaborative workspaces, which is different from other cloud providers like AWS or Azure, which generally provide virtual machines. In a nutshell, this means that you don't have to painstakingly set up your own virtual machines and work a lot in the terminal with command lines, but that you get a nice working environment that runs in your browser, which your collaborators can also easily access. And lastly, just in case, we are specifically talking about the HPC Research Cloud. Serve also has other supercomputers available for use, but that's more for a niche audience. If you do, however, need to make use of such niche services, feel free to reach out to them and they will help you. Now, why would you want to use cloud computing in the first place? The easy answer is to get access to more storage and computational power. In the cloud, you can quickly get access to computers that can have multiple GPUs, hundreds of gigabytes of RAM, and terabytes of storage. Something that is rather infeasible to invest into yourself as a researcher. This opens up many options with regard to data analyses, models that you can run, but also data sets that you can utilize for your research. Working in the cloud also allows for more easily reproducible programming environments. If you work on your local device, you will have a host of different installations, versions, updates, path edits, etc. Working in a virtual machine means you have a ready-to-go template that others can use to easily reproduce your results and methods, which is, of course, one of the pillars upon which science is founded. And, of course, having an off-premise device running its models in the background frees up a lot of time to work on your own personal device without it becoming very sluggish or running into problems because you need to catch the train whilst your model is not done running yet, so you need to turn your laptop off and then need to run. Might be a personal example. But in the end, it just frees up a lot of space and time, and it's generally just very convenient to use. So why would you use the Serve Research Cloud compared to, for example, a Microsoft Azure or an Amazon Web Services? Well, what really makes it stick out from the rest is its focus on being a safe and responsible research environment that is entirely GDPR compliant. Its servers are in the Netherlands. There's no dodgy data that comes in different countries that have very different regulations and are not fit for research purposes. No, everything's kept in the Netherlands, safe and sound. There's also a very easy front-end interface to use. If you've ever worked with Jupyter Notebooks, Jupyter Lab, or even just RStudio, you'll feel right at home. This is because the Research Cloud works with virtual workspaces rather than virtual machines, meaning that according to your wishes, different front ends can be put on top of these machines, almost like virtual Lego. This way you can work in an online environment that's very close to your usual coding workspace. And For more advanced users, it's also easy to remote SSH into the virtual workspaces like you would with any virtual machine. I'll showcase that later, but safe to say, the Surf team and your research IT department can put this workspace together as such that it's as easy to use for you as possible and as close to how you would normally interact with your software. Next, the Surf Research Cloud also allows for the safe and easy collaboration through workspaces, where the authentication is handled safely through your own research institutes, so you can easily add and remove collaborators also at will. And lastly, it's NWO funded, and there's lots of grants available to get free credits to use for your research. Most of these are for 1 year and can be renewed after, and are generally large enough to fit most research projects. This too makes the Surf Research Cloud a very accessible form of cloud computing compared to, for example, an AWS or an Azure. There's links in the description if you are interested in these grants. So, I'll shortly go through how to set up the Research Cloud. First, some prerequisites that you need in order to even be able to set it up. How do you set it up on the side of the institution, so your research institute? How do you set it up on the side of Surf itself? And I'll end with a practical example of where I utilize the Surf Research Cloud to run some natural language processing models. In order to make use of Surf's services, you need to be a researcher or have some connection to a research institute or an affiliate of Surf. Think of universities, University of Applied Science, like the Hogeschool Utrecht, the HU, or a Universal Medical Center, for example. This means it's also open to be used by students, teachers, or other positions within such connected institutions. And other than that, you will need just some basic programming knowledge. Like I already said, if you know or are familiar how to utilize Jupyter Notebooks or basic Python or maybe only some RStudio, that's more than fine. You won't need more than that. In order to get the Research Cloud set up on the side of your institution, you first need to set up a collaborative organization. A collaborative organization, or a CO, is more or less the cloud glue that binds everything together. It's under a CO that you make workspaces in the Research Cloud, add collaborators in SRAM, and you also get a folder under in Research Drive. And the CO is in the end what binds them all together. There's this helpful schema that we use within the HU that shows you what steps you need to take to set up Research Cloud and also, of course, to set up a CO. Where the first step is to fill in a request form for the HU Research Cloud, after which you get an intake with the Team DO, so the Team Digitale Onderzoeksomgeving, or the Research IT within the HU, and the Research IT department in the end helps you set up the CO and also request credits or a wallet for Research Cloud, and more on that later. And just to shortly show you what that looks like, this is datascience.hu.nl. This is where our documentation resides for example, how to request a Research Cloud. Here we see that in order to get a workspace in the Research Cloud, you have to go to the request form. That brings you to this website where you can fill in some information in order to request the access to the Research Cloud. After this, the Team DO will notify you, and generally within a week or so you're able to have a conversation, have an intake, and they help guide you throughout the entire process. And if you're already struggling a little bit with exactly filling in, for example, whether you have a research drive, yes or no, then you can also contact the Research IT department, Team DO within the HU, and they will help you further. To stand at this point for 1 second, so here it asks whether or not you have a research drive folder yet. If you do, you have to give the name such that it can be connected to the eventual Research Cloud. I'll show you in a bit when we get to the part of the research drive how to exactly get that. And if you don't have that yet, here's another request form for specifically the HU Research Drive, which just asks for the name and what kenniscentrum, what research center you fall under within the WHO, of course. This is the way you get access to the research drive. This is in the end dealt with by the data stewards within the WHO, and of course generalizable by, in the end, your research IT department. Then one of the first points to check is whether you already have access through your institute to SRAM, which serves Research Access Manager. It's the secure access platform where you will be managing your CO from, so your collaborative organization. It's the place where you'll be adding and or removing members from your CO, giving admin rights to also invite other people, or revoking those rights if it goes wrong. And I'll just quickly show you the environment itself. So this is SRAM, the website itself. It has a very easy name, just sram.serve.nl. And here you see that I am part of this specific collaboration. So this specific CO, which is just a pilot research to showcase the use of the Research Cloud. And here there are my fellow collaborators. I've blanked out their names because, privacy. But each of these have their own names and their own email addresses and certain roles. We are all admins, but these could also be, of course, non-admin roles, because you don't want everyone to be able to invite anyone else. In here, you also have join requests where you can, for example, using this link for membership request, send to people and then manually allow them to join. Or you can add, in this case, an admin, but also, of course, a regular user. You can invite them using their email address, select a group. If it says very little to you, ask for either Serve or your Research IT department what rights each of these specific memberships mean, which might be very important to have a good chat about. Also, what's their membership valid until? Is there a certain end date? Small message, and how soon they need to accept or decline your invitation. And then you just invite and then you're done. So that's how you invite members. One thing that's also happening through SRAM is the request itself for the CO. This is also something that your Research IT department will help you with. They will go through this specific form together with you to find out what name it's going to be, unique name, platform identifier, website URL, all this stuff. You'll go through together with your Research IT department to ensure that everything's okay. And then request, and that's fine. And lastly, what's also very important is here your profile. This is my email address if you want to contact me. And this is my username. And here we have my public keys. So here I just added all the public keys of my personal devices for which I want to use in order to get access to the Research Cloud. So if you want to use your own devices, for example, your laptop, and you want to SSH into the Research Cloud, so not using the interface of JupyterLab or of RStudio, but specifically via, for example, a code editor like VSCode, then you first have to add your public keys into SRAM before you're allowed to SSH into the Research Cloud. And then next up, the Research Drive. The initiator of the project, so the person who requested the CO in the first place, needs to also request a space allotment on their institution's Research Drive service. This too will likely need to be taken up with the Research IT department of your institution. Within the WHO, you should go to the data stewards and they will help you set up Research Drive. This Research Drive then needs to be connected to the Research Cloud environment in order to be visible in created workspaces, which I'll showcase in the next part, where I'll also show you around the Research Cloud itself. The Research Drive is best used as an easy means of sharing and or storing small files, so code, plots, output files, think in that area. For example, to ensure that your code also exists outside the workspace as a precautionary method, just like, for example, Git. but also to make it easier to share with your collaborators what you're doing. It's not as suitable to be used as a big data storage solution to run very big models on. It's rather slow in its read and write speeds. So if you want to run models on large amounts of data, it's much better to set up persistent storage on the side of the research cloud. And I will, of course, also go through that in a bit once we get to the point of the research cloud itself. First up, the research drive. So within the HU, we go there by going to hu.data.surfsara.nl. Lots of dots. And then what you're shown is this starting screen. I have a folder for each CO that I'm a member of. I am a member of one CO, the pilot of Ukraine, hence I only see one folder. Within this folder, I see another folder with some data and some files. For example, this small code tutorial that I'm currently building that I made in the research cloud and then exported to the research drive. It's still a work in progress, but this too shall be shared within the description. So you can also download this. This is just an example of how to use the research cloud for the small sample project that I did in it. In this file, you can easily share this with others. I'm only a member, so not an admin, so I can't share it to anyone else but people within the CO. There is this private link that you can make and share to others, and if they have access to the CO, they also have access to this file, and then you can easily share it like this. People can share comments about the files and also see what activities were done, like was it edited and at what time. I just created this a few days ago, so that's all the activity there is. One thing to be of note of already is if you go to the top right and go to settings, we will need the security tab in a bit, because at the bottom of the security tab is the webdev password, and this will need to link the research drive to the research cloud later. And then lastly, what we came here for, the research cloud. The first thing that's very important for the setup is to check whether or not you have your wallet approved yet from the side of Surf. So either via an A-infra request or a usual request through their website. This depends on what track you're actually going through, and also, of course, Research IT is there to support you in this. You will need the wallet before you can set up the research cloud, because otherwise there's no credits or core hours to use to set up workspaces with. So before you can really set up the research cloud, be mindful that you do need to have your wallet secured. So I will shortly go through exactly how to set up a workspace, but also how to connect Research Drive, how to create persistent storage in the research cloud, and how to connect it to your workspace, and also how to set up time-based passwords, log into the front end, etc., etc. So let's dive right in. First thing to do is to log in. You go to the Surf Research Cloud by going to the website portal.live.surfresearchcloud.nl. If you go there, you go to this login screen, which utilizes your own institution's authentication service, from Radboud University to, of course, the Hogeschool Utrecht, whichever institution you're a part of. I am part of Utrecht, so I log in via Utrecht, and I am in. The first thing to take note of is that I can create new workspaces here at the top, create new storage at the top, but as long as you haven't linked your wallet yet, all of this will be grayed out, and the only thing you can do is request a new wallet. And this is also the very first thing you should do. So if you click on request a new wallet, there are 3 fields to enter. The first is a subtitle. This subtitle, it doesn't matter exactly what you put in. This is for you personally to know what wallet you're using. So this could just be an example wallet. The second is the contract ID to which the wallet belongs. So in your e-info request, or the contract you signed up with Surf, it has an ID, and that ID needs to be in here. And then you have some remarks. If you have remarks, you can leave this empty. You click on request and the request is made, and then at a certain point in time you will get access through the ID of the wallet. And what you will then see here in the top, you can click on wallet, where again you can also request it. And this is, for example, the one wallet I have. So the title I gave it is what you see. And there's 3 connected budgets to my one wallet. So I have 10,000 core hours through this certain wallet. I have 50,000 core hours through this wallet. And I have 2 terabytes of storage space. You can also download your usage of your budget, so you know how much is left. And this is really the most important thing to do before you can do anything else. Next up, linking the drive, the research drive, to your research cloud. The way you do this is you go to Profile, and then you have your COs here at the bottom. This is the only CO I'm a member of, and if I go to this CO and click on Storage, I see that it's connected to the drive through this URL. So I have my research drive set up. Now, for the sake of this example, I'm going to delete this link to research drive. And then what you see is that the research drive is not linked, and I can click here to link the research drive to this CO. Great. The first thing to note is that you need to unclick this top box. This needs to be unchecked. So how do I get this information? Well, if we recall what we looked at the research drive, so again, you're in the research drive, you go to settings at the top right, you go to security, then at the bottom you have web dev passwords. The first thing you want to do is copy the link here at the bottom and replace this URL at the top. Username has been set correctly. You can also check that through general. Yeah. Username fabian.kok@hu.nl. Yeah. Username is correct. And then the web dev app password. So I go to security again, go to the bottom. I give it a certain app name. I used Ukraine. It's fine to just use that again. Create new app password. Again, I see my username here. That's correct. I copy the password, paste, save, done. So now my drive is linked to the research cloud. I'll show you in a bit how that exactly looks, but this basically means once you set up a new workspace, your research drive will just be a folder in your workspace like any other folder. So it will be super convenient to use. This is how you set up your research drive. Next up is how to set up persistent storage. So this is something you would want to do if, for example, you're training a really big model in the cloud that needs a lot of data that doesn't take too long to read and write to. The research drive would not be very sufficient in this regard because it has slow read and write speeds, but the HPC storage solutions that Surf offers is very beneficial for this purpose. So, how you set this up? You either go to the storage tab and click the add button, the plus, or you just click this create new storage button at the top. You choose persistent storage on HPC. You choose the collaborative organization, the CO you fall under, or that this specific project falls under. I have only one, so that's the one I select. Then the available wallet. I have only one wallet, but if you have multiple, select the wallet that fits the CO. Then the cloud provider, there's specifically one, so that's the one we choose, the HPC cloud volume. And then we choose the amount of volume that we actually need. This ranges for me between 50 gigabytes and 1.5 terabytes. The options you see differ probably depending on what agreement you have with Surf and what your wallet actually gives you access to. If you need more than what you're currently seeing, for example, 2 terabytes, which was in my wallet that I have up to 2 terabytes of volume, for example, take this up with Surf and maybe your research IT department, and they will help you get that settled. For now, I could just choose 50 gigabytes, continue. We can give it a name. This can be any name you want, and some description, only then correctly typed. You are very aware that the workspace will be paused automatically when your contract expires or your wallet is depleted. And you have, of course, read and agreed to all the terms and conditions. Now, you click submit and your storage will be made. I've already made some here, called the example HPC storage. And the gedelt data is what we used for the example, which we'll get to in a bit. So the information we see here, we see who owns this storage, whose wallet it comes from when it was created, what CO it falls under, and other collaborators within the same CO would be able to see this storage. So multiple people can utilize the same data storage unit. And here it is saying it's 0.5 gigabyte big. So then when I'm setting up my workspace, which I'll show up next, I can choose this storage, immediately connect it to my new workspace, and then have access to it like I would have, like the research drive, like any other folder. You set this up when you create a new workspace. It's much more difficult to connect it to an existing workspace. So be mindful of that. That's also why I show this in the order that I do. First, link research drive, storage, and then start setting up your workspaces, which we will show next. So now that we've set up the wallet, we've set up the link to research drive, and we've created storage, it is finally time to create our own workspace. We can do this either in the workspace tab here below, click on the plus, add, or in this big box at the top, just create new workspace. We then have to choose an application we want to use. And an application, like I referred to in the past, is like a Lego block that has been put on top of an already existing infrastructure, like for example, Ubuntu or Windows. If, for example, we go to the second tab, we see here a Jupyter notebook, or an RStudio, or a Jupyter notebook with CUDA, or a Jupyter notebook with an R kernel. Depending on your need, multiple different types, multiple different applications have been built to make it easier for you to interact with the cloud environment. Of course, if you like Ubuntu more bare bones, so just straight Linux distro, you can also just take Ubuntu 18 or Ubuntu 20 with or without sudo enabled, or Ubuntu desktop even with CUDA. Whatever you need, it's generally available, and otherwise if you have different needs, tell them to Surf or your research IT department and they'll help you out. But for our current purposes, let's just say we want a simple Jupyter notebook. And we want to do this within the CO that we're currently working. So for me, that is this specific CO. If there is a dataset that has been made publicly available to you, then you would see it here and could utilize it. No such datasets have been made available to me, so I can't select any. For my cloud provider, I'll use the wallet that fits my CO. It's only the only wallet I have. We're looking at the HPC cloud, so that's the one we select. And then we have different flavors that the application has been built upon. So we could do a very small or medium virtual machine, like it's built on Ubuntu 20, great. It has 2 CPU cores, 16 gigabytes RAM, and it uses 48 credits per day. So this is a pretty small machine that you can run for quite a while. I think the general contracts for a year pilot at Surf are about 50,000 credits for a year. You could run this then for 1,000 days before it runs out. So it's a very safe option to just run, and you have to not be too mindful of whether or not you paused your machine, yes or no, which I'll showcase also in a bit. Say you want a bit more power, you've developed your algorithm on a small batch of data on this medium VM, and now you want to go to the big guys. You could, for example, grab one of this 30 CPU core, 480 gigabytes of RAM machine. It uses up way more credits in a day, but this is, for example, where you would do your big modeling. For now, let's just say we want to go with a smaller machine, and that's the one we set up. And then there are certain options that you can add. The one that I will be adding is some storage. And what I want to add is this example HPC storage that I created earlier. So this is, I didn't give a description, so no description has been found. But this is the 50 or 500 gigabyte storage that I made available to myself. So I select that one. It has been selected. We continue. Then be very mindful of the expiration date of the machine, because on default, it puts it just a few days ahead and that's it. This is, I'm currently sitting here on Monday. It's only the same week basically that already says it expires. Let's not do that. Let's say at least till the end of the year. Then we have to give the name. So this is just an example workspace. And it needs a host name. This needs to be unique, but you can put in whatever you want. So this could be example works, because I'm pretty sure it will run out of characters. Yeah. And here you can also, of course, still give a description, a small description of workspace. I am very original. Again, I am aware that my workspace will be paused when my contract expires or wallet is depleted. So if you run out of credits, then the workspace will be paused. Makes sense. And you, of course, read and agreed to all the terms and conditions. Great. Then it will take some time to set up. Generally 5 to 10 minutes, depending on how big the workspace is. I'll see you guys when this is done. And now that the workspace is done loading, we have a workspace here. So we have our example workspace, which we can rename if we want to. And we can examine exactly the details of this workspace. We see when it will be removed. So that is the 31st of December. We can change this if we so desire. What wallet has been connected, under what CO, what's the drive that it is connected to, etc. Now there is one last thing to set up in order to get into this workspace. If you want to get into this workspace via the Jupyter Notebook environment, so via this access button, we will need to get, first off, a username, second off, a password. The username part is rather easy and simple. The username is if you go to your profile, so go to the Service Cloud, go to my profile. Here I find my username, so I can just copy and paste that into here. And then the password. The password you get through profile options. If you haven't done this yet, this is where you can set up a time-based password. So if you haven't done that yet, this will not say reset time-based password, but set time-based password. It will give you a QR code. You scan that with your authentication app, like for example, Microsoft Authenticator, and then you have a password that refreshes every 30 seconds. That is the password that you need to input into JupyterHub. I will do that now for myself. There. And then we get to this screen. Sometimes it shows up like this. Generally, if you then just refresh, it should actually get you into the JupyterLab environment. And we are in. So this is currently in the research cloud. What we see here, we can make notebooks, like an IPython notebook. We can go into a Python console, or we can set up a terminal, make a markdown file, etc. Here on the left, we see our folder structures. So we have our data, where this volume, which we'll examine in a bit, is the data that we've connected, so that extra 500 gigabytes that we connected. And we have the research drive, where we see here the CO. And this has all the files and data that's also in the research drive. And this is just as easy to connect to now as any other folder. We also have Git. So if we want, we can open or initialize a Git repository. And there's also extensions that you can enable for example, Git or other different types of extensions. If you need more, you can of course either set this up yourself or just ask your research IT department or SURF. But this is the basic interface via JupyterLab that you can work in. I can just create an example notebook here. Let's just do the usual. Hello world. I can run. There, I now have a Python notebook. I can save it. I can rename it or do anything with Git, download links, etc. I'm just going to rename it to an example notebook. And even though I just put it here on the research cloud, if I want to get it on the research drive, I could just cut and paste, for example. Okay. Go here, paste. And now this example notebook is working in the research drive. So if we would now go, for example, to the research drive, and I go to the pilot folder, and I refresh, and there it is. So now I have my code that's in the research drive. I can edit it, export it, whatever, through the research cloud. And I also have access to this extra volume of data. Just to showcase this, I could, for example, open a terminal and I could check how much storage space I have. And let's do this in gigabytes to make it a bit more clear. This is the setup. And here do we see the extra connected half a terabyte or 500 gigabytes of storage that is set in data volume 2. So I have now access to this fast, big data storage that I can just put my data on. I can remove this workspace and this data will still be safe, kept in the Service Cloud. And then create, for example, a new workspace on top of it. This is especially useful if first you build a small virtual machine, a small workspace, to first build your initial model on and only then afterwards build the big machine. You have this persistent storage, so your data is safe. And again, if you want, you can use a notebook environment. If you want, you can just have a Python environment. And like this, you can also, through terminal, through pip, for example, get access to installing packages or whatever. If you do need to do more installations, like for example Miniconda or anything similar, you can also do this yourself, or you could ask your research IT department to help you set that up so that they already put it in once you create your workspace. So that is the basic environment. You can now start coding here. You can export to your local data drive folder, to the research drive, and it's all now connected into one easy to use environment. Then we've gotten to the practical example. we would like to showcase here how you can utilize the Research Cloud for specifically modeling purposes. So what we want to showcase exactly is, first off, how you can read in loads of data. So for that we use the GDEL dataset, how to store this in the Research Cloud, train a model on it that requires quite a lot of resources, and then how to export these results to the research drive. The exact results themselves are not that interesting, and they're also very much not the focus here. It's the method of work that we utilize that we really want to showcase. So how would you be able to use the Research Cloud, Research Drive? How would you use it in practice? Well, to start with, going to my workspace, I have this machine that I used for running the model. I called it Ukraine Development Beast because this is the really big one that had a GPU and an A10 in it, and had about 100 gigabytes of RAM, 86 gigabytes of available RAM, which in the end, I actually needed every inch of that. So this is in the end where I ran my model in. The one that I used for purely developing on a small data set was this smaller VM. This was had 16 gigabytes of data on the top of my head, and I think 2 or 4 CPU cores, which was more than good enough for developing the small scale model. But once that was done, I ran it on the big boy here. So the data we used was from the GDEL dataset. So the GDEL is a global database of journalistic articles that are being published every day, and they're trying to consolidate all those articles, also doing lots of modeling, semantic analyses, etc., into a BigQuery public dataset. This is available to everyone to take information out of, and that's also what we wanted to do. So, if you're interested in this, I thought I would shortly walk through how you can get this data for yourself or similar data from Google BigQuery. Because I found it actually, when I dove into it myself, not that straightforward and clear. If you go to console.cloud.google.com, so basically the Google Cloud, you get to where you are right here, and then you want to go to the BigQuery. So, and then specifically the SQL workspace. This is the main hub for Google BigQuery. And if you want to explore some data, and especially public data, you can click on Add Data, and then go to Public Datasets. And this shows you all the public datasets that are available. Well, we were specifically interested in the GDEL dataset, which is this one at the top, the GDEL 2.0 Event Database. And you would assume that clicking on View Dataset would easily allow you to view the dataset. You might be a little bit wrong there, sadly. If you click on View Dataset, you see it is something that exists. It's called GDEL v2, but you can't really at this stage interact with it in any way whatsoever. So the way you do that, I had already started here, but let's remove it. You go to your search bar, you type in GDEL or the name of this public dataset that you want to look at. You click enter. Then it finds some results because I've made some things, but it doesn't see the public dataset yet. You have to first click broaden search to all. And then it shows you all the datasets. This GDEL BigQuery is the public dataset. And GDEL v2 contains all the interesting datasets. And in here you find lots of subsets of the GDEL dataset. For example, you have the GQG, the global quotation something. And this, for example, you can click on preview, contains quotes of articles that are being published worldwide. This is not in English. They also have a translation module if you're interested. But this is the way that you can query in BigQuery the GDEL dataset, and on the GDEL the website themselves, you can see through documentation what exact data sets they have available, like the knowledge graph, Cadell 2.0, and through this documentation you can find more information about all these data sets that you see standing here. The one we used for our analysis was the GGG, because this had this interesting field, the contextual text. So this contained a condensed version of the text of articles. So this is the text we wanted to use in our NLP program. So we wanted to do BERTopic modeling, and we wanted to do it on this specific contextual text to see if we can find some interesting topics that were coming up in the war with regards to Ukraine or Russia. So this is the data set that we wanted to use. Now, if we want to view more of this data set, you are able to build queries. So let's say I want to build a new query. You can select everything from the dataset. This only shows the first 1,000 entries. You can run it, and this will give you back a temporary table of information, where here it doesn't find anything on this specific date, but probably if we go back 2 months, it does actually find some. There we go. So this gives you a small resulting data set from the query you inputted. Now, if this becomes too large, you won't be able to view it in this kind of temporary data set, and you need to actually save this data set. So what you then have to do is you go to query settings. You have to create a destination table. Click create new dataset. Give it an ID, give it a location, create dataset. I've already done that, so we won't. And then save, and it will start a job, and it will save your data. Well, that's something that I already did up here. So I created this table, this export table. This used one specific query. So it used this saved query of Dane export. So this is in the end the query used to get the data that we wanted to use for our analysis. So we wanted to take all the features from this GGG subset of the dataset, where the date was between the 1st of January and the 18th of October, because that's when we started doing our analysis. And location would be either the Ukraine or Russia. So the location they were talking about within the journalistic articles would be either the Ukraine or Russia. So this was in the end too big to just put in a temporary table and then export. So it had to be put inside this export table. Just like I showed you just now, via query settings, I put it into export table as a dataset. And that's when I got this specific dataset back. If we look at the details, we find it's about 45 gigabytes big, which is already quite a lot of savings compared to the 2.5 terabytes they actually have on there every year, and much more manageable. We'll find that even this dataset, when using BERTopic modeling, that it's already kind of on the edge, even if you have 100 gigabytes of RAM. Because BERTopic modeling really wants to keep everything in memory, wants to use everything at once, and it generally doesn't like doing batch processing where you first take a part and then train over the next part. Generally seems to work less well. So 45 gigabytes is actually already quite a lot. And then when we have this here, this table, we at least have our results saved. So we have not been able to export it yet outside of Google BigQuery, but we've been able to save our query to BigQuery. So this has all the information that we actually want to get out of BigQuery. So when you actually want to do that, you want to export it to Google Cloud Storage. So we go to Browse, and here, if you haven't done so yet, you can create a new bucket, which is basically just a set aside portion where you can put data in and also get data out. I created one bucket called the Ukraine Gdelt export bucket. I already created an extra folder in here. You can create more folders if you so wish. And in here you then put the name of the files. Do be mindful that they will be split in multiple smaller files. So we could say Gdelt GGG, that's fine, and then just an asterisk and the file extension, so .csv, and let's say we also wanted gzipped. This asterisk means that for every created file, it just inputs 00001, 0002, 0003. So these files in the end will be Gdelt GGG underscore and then a number, and it will just incrementally increase that number for every new file created. Be mindful that the file extension, so here for example I say CSV and then gzip, that it actually matches your export format and compression if you do use that. Otherwise it will, for example, say I would not gzip it, but I would put it in here. It would not give me an error, it would just very mindfully just do everything I tell it to do. So be mindful that your file extensions are actually correct. And then you press save, the job starts and it starts exporting all your data from this export table in Google BigQuery to a bucket in Google Cloud Storage. Well, that's also what happened. We went to Google Cloud Storage, go to bucket, leave. Here I have this export bucket with this folder that we saw previously. And for ease sake, I kept these all at CSVs without compressing them into gzip files. And here you see each individual file. You can manually download it, but of course you can also very easily write a script that can download individually each of these files and put it into, for example, your Research Cloud. So say you have some persistent storage in your Research Cloud workspace. So if, for example, I would grab my workspace, I have it here set up in VSCode. I look at my data and I have here extra data sets. So this Gdelt dataset volume 2. For me, it's already filled, but say it wasn't filled yet. You could easily write a script that would put data inside of this persistent storage. So that is more or less how you get that data into your Research Cloud workspace. And we now get to actually do some modeling. Well, to first shortly show you around my personal workspace, I SSH into a workspace created on the Research Cloud. You can see this in the lower left. So I have SSH into what I've called the Ukraine Dev Beast. This is this specific workspace. So I use this IP address in order to SSH into it. So if I open my configuration file, it's this specific one. So I gave it a certain name, which is the name you see. I added the IP address, as you can copy from Research Cloud. And I inputted my username, which you can get from going to your profile. Username, fcoc2, and I inputted that in here. And of course, very important, adding your public SSH key in sram.surf.nl in order to actually be allowed and authorized to access the workspace. So once I did that, I also had the research drive linked via the CO. So if we go back here, we see the CO. We see in storage that the drive was linked. So that is in here. I see here the name of the CO. And here there is some small amounts of files and data inside. Accessing this is for me as easy as accessing any other folder as you would on a regular computer. And aside from this, I have also got this Git folder where I actually have my code inside of and some generated data, some pickled files. And this immediately connects to source control in Git. So I can very conveniently, just like writing code on my personal devices, am able to work the way I normally do. And this folder is just as easily accessible as a research drive folder as any other folder inside the cloud. And then lastly, my data is in here. I have this data folder, called it Gedelt, and in volume 2. And here I see all the CSV files that we imported from the bucket in Google Cloud. So that's my basic setup. If we look at the code, this is a documented Jupyter notebook in progress that I'm also sharing with everyone. It'll be a bit more of a puzzle how to share these pickled files such that you don't have to train the entire model yourself. Of course, you can always send a request in the email and the contact information in the description, and we will try to get this data to you. So to shortly walk through what we did in this example, just to showcase how you could use the Research Cloud, we first, of course, imported the packages that we needed. So this included some OS stuff to get the data from the data folder all together, and pandas, of course, to transform. Pickle in order to save and load pickled files, which is incredibly convenient. And for modeling purposes, some BERTopic packages and NumPy. The first thing that we did was to get all the paths to the files of our data and then concatenate these into one large data frame. This took quite a while, especially because these were not gzipped, so the files were even larger. This took, on this specific machine, which has about 100 gigabytes of RAM and quite a lot of CPU cores, it still took about 20 to 25 minutes to piece everything together, because we have about 190 different CSV files that all need to be concatenated together. This is also very much not the optimal way to do it, but it is an example of how you can tackle this. Just for ease sake, you can also just read in the training data already at the start using Pickle, just to make it more convenient to actually test out how things work and continue from where you left off previously. So this is just some very minor pre-processing that we've done. Generally, using BERT and hence also BERTopic modeling, you don't want to pre-process your data and your text too much. Generally, you even want to keep in words like the, in, because this also gives context to words. Of course, depending on the topics you actually get out, you might actually want to try whether you get more consistently good results leaving such words out, but generally you want to do very minor pre-processing of your text before you start using BERTopic modeling. The minor amount of filtering that we did do was drop duplicate titles. What we saw in the data is that there was quite a lot of duplicate titles, maybe because they were all published within a few minutes of each other in various territories, and then all of them got into the Research Cloud. There were quite a lot of duplicates in that sense, so we dropped those, and we dropped all rows that had a missing value in some important features. And we dropped all features that we didn't care about. And then this very much helped limit the data set, make it about 35 times smaller. This just very much also helps to keep the model from exploding, as we will see a little bit later. In the end, this would then become our training data. It needs to be in a list form, great. And then here is a way to easily save it into a pickle file, which I would highly advise you to do so. Also very much because Jupyter notebooks are horrendous with doing proper garbage collecting. Because even when you start deleting data points in order to free your RAM, because spoiler alert, when I tried to run this the first time, even on this beast that had 86 gigabytes of RAM left over, it ran out purely because it did not have enough space. And the downside with notebooks is just that they might take up, for example, by reading in this data at the top, continuously 20 to 30 gigabytes of RAM. Even though you don't use it anymore, even though you try to remove the data, it still is there. So what helps then is to just pickle dump your training data, restart the kernel, and then only take the pickle load in order to get your data in, and then you don't have this problem with 20 to 30 gigabytes of RAM just being used for nothing. So next, we set up our model. There are many embedding models that you can utilize. This specific one is the default because it has a decent balance between speed and quality of topics that it gets out. We put calculate probabilities to false because putting this to true, if you have more than about 50,000 articles, it costs way too much computing power. And as we have quite a few more than 50,000 items, say 28 times more, we put this as false. So we don't get the probabilities of all the topics that are being found. And I put verbose to true because I find it useful to actually see what's happening in the model. And especially if it takes about, this took about 2 hours to run. It's always great to see actually what is currently working on. Then all that's left to do is just fit transform to the training data. And it's also, especially because it takes quite a while to run, I would also advise you to save the model such that afterwards you can still easily run it. Or, for example, share this data and let someone else also run the model without them having to train it themselves. And here is just some method to also load the data back in. So this took our model about 2 hours to train, utilizing the majority of its 86 gigabytes of available RAM. This is very much due to this also a model I wouldn't have been able to run either at my desktop, even if it's quite a beefy one, or my laptop. Which is also just another convenience of the Serve Research Cloud. And then in the end, we can get some topics. At the start, this found about 11,000 topics, which is quite a lot. But luckily, BERTopic Modeling also has a method to reduce the amount of topics. This is also quite a costly operation though. And you can't increase the topics afterwards, so you can only go down the number of topics. A good estimate more or less for us was to look around 100 to 50 topics. It tries to dynamically patch together topics it already found that are the most similar to reduce the amount of topics found. And of course this is also just a bit of a trial and error to see what gives you the best results. And if we go down, we see a method to visualize the topics. This is just very easily done too. You get this plotly plot that easily allows you to zoom into topics found, like for example this cluster, to more easily see what has actually been found. It shows you what words the topics consist of and how many times it actually appeared in the dataset. Pretty easy, convenient visualization. You can do many more visualizations. There's also dynamic visualization, so you can also do dynamic topics. So if you add timestamps into your data, you can use the trained model and those timestamps to see how the topics evolved in certain batches of time, which is also very interesting, especially if you start looking at certain events in the war and how that changed the perspective of media in, for example, the Ukraine and more the Western countries, Russia, and maybe more neutral countries like India. So there's a lot of possibilities here. Also, of course, in the pre-processing of data, currently it's looking for topics for Russia and Ukraine combined. It's very likely you want to split those up and look at also other countries. How are they actually looking into the war, looking at certain domains of where the actual journals are publishing from. There's many more interesting angles, but this is just a showcase of how it could work. And then once you have made such a visualization, you can save it into a figure and then write it out as HTML. So this links to the research drive just as easily as any other folder. You name the file. I called it model visualization 50 topics because it was with 50 topics. And that's it. You see here in research drive, it exported it to here. So if you look on the website, we find this model visualization here. We could easily download it, share it with others, open it, and then we have our topics and our visualization very easily available in Research Drive. And then we can do exactly what we just did. And it's easily shareable. And that's it. Thank you very much for your attention today. If you want to get in touch, there is more contact information down in the description. And otherwise, I wish you a very nice day.